Hello. Hello, Karishma.
Hello, uncle.
Hi, how are you?
Fine.
Good. Okay, so how things are? Prepare.
Things are fine. I think 12 started for us. So
Okay,
yeah, we have school till 19th.
until 19th. That
Yeah.
is another 3 days.
Yeah.
After, how long will be the break?
A break, I think we have like 1 month. So June 5th it reopens.
Okay, so and then they will continue. So they already started, but they will
Yeah,
continue.
they'll continue in June.
Okay. So anything in particular you find it we need to discuss or any problem you find it better to have a more discussion so that the understanding can be better like that.
In physics, electrical charges.
Okay.
Yeah.
Okay. 1 second. Let me get a whiteboard. Did we discuss about the charges and what is a electric field and electric force? Anything you
No.
discuss like that?
No.
No. Okay. Okay then. So we completely start from scratch and then we take it from there. Is that okay?
Yes, uncle.
Okay, it's all about, physics is more beautiful, like, because it's an application of the mass modeling and everything. So let me share the whiteboard first. Okay, so, but we completely done the, when a mass object with a mass is there, around that, there will be a gravitational field. Do you remember that?
Yes, uncle.
So we take a, let's say, can you see the whiteboard?
Yes, uncle.
Okay. So let's say there is a mass with value m. Then from its center, let's say you go to a distance where we call that as a, let's say the distance is r. And it is going to have a gravitational field around that. And then when we go away and away and away, the magnitude of the gravitational field is getting reduced. So if you go really far away from the particular mass, you won't feel the gravitational field generated by the produced by the that mass will be completely gone. Do you get that? If you go
Yes.
mathematically, if you say the r is going to infinity, you will get a 0. But
Yes.
for all purpose, we know that this g, the g is a vector, which is the gravitational field strength. Its direction is towards the center of the mass. Do you get that?
Yes.
So this we know that it is directly proportional to the mass of the particular. If the mass is bigger, then the gravitational field strength will be bigger. If so the direct proportionality, we know the meaning. And also it is inversely proportional to the square of the distance from its center.
Yes. Yes.
Okay. Then what we did, combining these two, you put a single proportionality, which is m over r squared. Then we said g is nothing but our capital G, universal gravitational constant, multiplied by m, mass of the object, divided by its distance from its center. Is that okay?
Yes.
So one of the simple application could be, let's say, take the big mass which we are living on. Let's say from the center of the earth, the mass is capital M, and on the surface of the earth, already from the center, there is a distance capital R.
Yes.
So the G, which is going to be generated by the gravitational field strength produced by the earth with a mass capital M on the surface will be equated to capital G, capital M divided by capital R square.
Yes.
We know that G is a constant that something like 6.67 into 10 to the power of minus 11. And the mass of the earth, if you know, and the radius of the earth, we know, plug it in and everything, this will come to 9.8 meter per second square. Okay, this is what we use as our, then we immediately put, because there is a related next quantity. What the next quantity? When there is an acceleration or an gravitational field produced by mass, an object. Let's say we put here, we just make a, so we just did this job from the M. Now let me call that as a M1. Already it has generated here. There is a G produced by this M1 will be equal to towards that center. Do you get that? The direction is, I will put a unit vector here. So all purpose, I will put here, this is a G cap, so that I can write it as a G cap here. Is that okay? That will make more
Yes.
sense. Okay, the direction also for the vector quantity towards the center of that. So this is going to be a created by the mass M1. The G M1 cap will be in this direction. That will be given by our capital G M1 divided by, let's say this is our R. That will be R square, right?
Yes, sir.
Be multiplied by G M1 cap. Let's say now bring another mass, which is value is M2. So what the gravitational field strength produced by the mass M1 will be felt by the M2 will be a force of attraction towards the M1 center. So M2 will feel a force of attraction. Do you get that?
Yes, sir.
Force of attraction towards M1. Towards M1 center. So now, how to quantify that? So let's say that is a vector quantity F, force vector felt by the M2 mass because of the M1 gravitational field strength is actually equal to whatever the M2 mass multiplied by the gravitational field strength produced by the M1 at the place where M2 is sitting. Is that okay?
Yes, sir.
So this will be, now if you substitute that GM1, it will become M2 multiplied by capital G M1 divided by R squared GM1 cap. So this will look like, we can rearrange that so that it will be a G M1 M2 divided by R squared G M1 cap. Is that okay?
Yeah. Yes.
So the same situation, we could have put it in the other way. Let's say originally there was a mass M2 and at a distance R, it would have generated its own gravitational field strength, which will be GM2 vector quantity, which will be direction will be towards its center. That will be GM2 cap unit vector in that direction. Is that okay? So this would be given by capital G M2 divided by the radius, the distance square G M2 cap. Okay. So here, as the equal and opposite, we can always write G M1 cap unit vector is exactly equal to minus G M2 unit vector. Is that okay?
Yes, sir.
Because they are only direction, so the direction is exactly opposite because we are talking about looking from the M1 point of view or looking from the M2 point of view. That's it. So now bring in the M1 mass and put it here because there is already a, so M1 if you bring it here, the M1 will feel the force of attraction towards the M2 center. So that force M felt by 1 because of the 2 is going to be the mass M1 G M2 vector, which will be equal to M2 M1 capital G M2 divided by R squared G M2 cap, and this can be written as minus G M1 M2 divided by R squared G M1 unit vector. Is that okay?
Yes, sir.
So whatever the magnitude of the force felt by the mass 1 attracted towards the M2 will be exactly same as the magnitude of the force felt by the attractive force felt by the M2 because of the M1 gravitational field. But the direction alone will be exactly opposite. Is that okay?
Yes, uncle.
So all this understanding everything, we can completely the same thing. We are going to use it for the electrical charges, but this is all gravitation. Under the gravitation, we have done this. Main important point, the difference between this and two, there are two things. First thing is the mass is a scalar. The mass is written as a m, which is a scalar quantity. Do you get that?
Yes, uncle.
It has no positive or negative or something like that. Even single dimension direction is not there in the m mass. Mass has nothing to do with the direction. Do you get that?
Okay, yes, uncle.
Okay, that is very important because when you go for the electric charges, there are going to be naturally there are two kinds, and that is going to complete analysis and mathematical modeling. Everything is exactly the same, but the first difference would be, we go to the new page.
Yeah.
Okay, so now electric charges. Electric charges. So here the charges have two types. So we have a positive and a negative charges. Okay.
Yes, uncle.
So that is going to make the things bit interesting because in the mass, the gravitational field and the gravitational force will be only the attractive type. Do you get that? Towards the center of the particular mass we are talking about. Now things can be two different possibilities are depending on whether it is.
Uncle, just 1 minute, 1 minute. Yes, uncle. Sorry.
Okay, so there are two kind of charges. Keeping that in mind, we will bring the positive or negative bit in a minute. So take there is a charge Q. So from its center, so what is going to be exactly what are all the things we have seen in the gravitation? Around a charge, there will be electric field. There we call that as a gravitational field. Here we call that as an electric field. Is that okay?
Yes, uncle.
So if you go to a distance r from its center, then it is going to produce an electric field there. Again, with the same understanding, electric field is going to be directly proportional to the quantity of the charge, and electric field is inversely proportional to the square of the distance, and there is a E cap also. So that will be depending on the Q is positive or negative, the direction of the field will be different. Because we have to identify that, right? Because mass wise, it is always attracting towards the center. The direction of the field, gravitational field was always towards the center. But in this case, we have two types. If the charge is positive, we have one kind of positive electric field around that. If it is a negative charge, then it is a negative electric field around that. Do you get that?
Yes, uncle.
So positive electric charge, as it is a positive, already we defined it for the charge type itself. That will be a positive electric field. That is classically or traditionally, we took the direction as away from the center because something like the positive negative, right? The number line from the from the zero to the right side, we always say that it is going away from that. So it is, if it is a positive charge, it will be so. I will write both the things. Let's see whether you understand that. So I will write here one going away, which I call that as a E field positive cap. Going inside, it will be a E cap negative. Does that make sense for you?
Yes, uncle.
Okay, so this is the positive charge, positive charge. That is Q is greater than 0. Here, the Q is, this is negative, that is Q is less than 0. That's the difference. First difference. Is that okay?
Yes, yes, uncle.
And then one more second main difference in the electric field compared to the masses, the gravitational field. In the case of masses, we cannot allow any other mass in doing this particular calculation. You get that? The gravitational field means we say that this particular mass is completely away from any other mass. Otherwise, the whole thing will get changed. Do you get that?
Yeah, yes, uncle.
So if you talk about even some small object like a mass, and around that there is some gas medium like a air or something like that, they all have tiny molecules, but randomly they are around it in the uniform density, uniform distribution. So one is, all of them will produce a very tiny gravitational field. They will cancel each other. Do you get that? Because they are uniformly distributed around the object we are talking about. You see what I'm saying?
Yes, yes, uncle.
Okay, so only when the gravitational field produced by the object around that is comparable to the mass, then we need to consider. Otherwise, if it is a very tiny mass like some gas molecules or something like that, we consider that is very negligible, and that is not going to influence the calculation. Do you get that?
Yes, uncle.
But here is a different story, because the charge we are talking about, the material, the medium around the charge, that electrical property of that medium will play an important role. What that meaning is, because they have their own, even though the medium could be insulator, but there is a nucleus, proton in the center, and electrons going around that, and the construction of whether they have free charges and everything. Based on that, it can be conductor or insulator, all those type and everything. Even if you consider as the insulator, they will have a electrical property. Do you get that?
Yes, uncle.
So we cannot ignore that. So the electrical property is very important. So the electrical property, we call that as a permittivity. Permittivity, which is denoted as epsilon. Okay, so this is called epsilon. So why the name even permittivity is, when we are talking about the electric field, there is a insulating material around that, and it has to permit the electric field to pass through that. Do you get that?
Okay. Yes, uncle.
So that is why it is called a permittivity, and we use the epsilon. Now let's say there is a medium around this particular charge which has a permittivity epsilon, then the electric field is going to be proportional to 1 over epsilon. Okay, combining all this thing, we can write E is proportional to Q1 Q divided by epsilon R square.
Yes.
Let's come to the point of the Q. We already know when the Q is high, the E will be high. As we move away and away from the charge, the electric field will reduce. That is why E is proportional to 1 over R square.
1 by R square, yes.
But now we are saying that the epsilon is the permittivity of the medium surrounding that Q. Why the electric field is inversely proportional to the epsilon? We want let's say, if the material itself is going to use the electric field generated by produced by this charge for some purpose, then at a distance R, the electric field will be low value. Do you get that?
Yes, sir.
Let's consider two medium. Let's say the same charge at the same distance R. We are talking about an electric field generated by the charge Q at a distance R. Take first scenario. There is a medium where it is going to completely not going to make use of the E at all.
Yes, sir.
And there is a medium is going to make use of the E a little bit. Don't you think that the second medium will make the electric field created by the charge Q will be lower value there, right?
Yes.
So from the physics point of view, from the electricity point of view, we can ask a question, what the medium is actually in the name of making use of it. Do you get that? So already we are saying that, okay, let's come to that bit when we see the electric force also. Do you get that? So all we are saying that if the epsilon value is as low as possible, then we will have a better electric field amount produced at that point.
Yes.
So if the epsilon goes higher and higher and higher, then the E value will go lower and lower. And for example, if the epsilon goes to really high, go to infinity, then there won't be any electric field at all at that point. Because it's 1 over epsilon, right? 1 over infinity is a 0.
Yes.
So that means what? Even though the Q has produced some electric field, that is completely used by that particular material, which has a very high epsilon value. Does it make sense for you?
Yes, yes, uncle.
Okay, so let's get to that. What is the meaning of making use of the electric field by a material very soon? Okay, so now we have the job to do. So we have the E. I put the E cap in general. Okay, and you know you can put the positive or negative. Depending on that, it is going to change the. If it is positive, yeah, those things. So now we have to equate this. First of all, when you equate it, we are going to understand here in a way that actually when you see, because all these things comes from the Coulomb's law. Okay.
Yes.
Coulomb, he just it is similar to the Newton's law and everything. He never brought the epsilon into the picture. It's not that completely, but he never wrote the electric field can be proportional to 1 over epsilon was not, even if you take any textbook, anything in the internet, anywhere, nobody will talk about the electric field is proportional to 1 over epsilon. Do you understand that?
Yes.
So they would have stopped it like E is proportional to our Q over R square. Is that okay? Q over R square. They will stop it there. So they would have, from here, they would have gone to, then if you equate, there will be a proportionality constant, then multiplied by Q over R squared. Then they would write the K is nothing but 1 over 4 pi epsilon. They bring the epsilon there, which I don't like, because when you say K is a constant, then how come the K can change if you change the medium around the Q? Do you see what I'm saying?
Yes, yes, uncle.
Okay, so when I equate the equation which we have drawn as a proportionality, I would say straight away the constant is 1 over 4 pi. That's it. Okay, Q over epsilon R squared, E cap. Is that okay?
Yes, uncle. Yeah.
Okay, so now make a bit of a small arrangement, change in the way the expression looks. I will bring the R square next to the 4 pi and write the epsilon separately in the denominator. Is it ring a bell? What is 4 pi R square from the scenario of this Q at a distance R?
4 pi R square is the surface area of a sphere.
Okay, now think about it. Yeah, there is a charge and you go to a point which is R distance from the center, but that R could be used as a sphere and that could be anywhere on the sphere surface. Do you see that?
Yes.
Okay, so I'm just saying that the Q is here and we are going to take a radius and you form a sphere.
Yes.
So don't you think that from the center, the electric field is expanding in a spherical way? Dimensional point. So don't you think that it is reducing not directly the R square, it is reducing on the surface area of the sphere, right?
Yes, yeah.
So if this is our R, then we say the surface area is going to be 4 pi R squared. So this is the right understanding. Then I would say a electric field generated by the charge Q at a distance R, that field is proportional to the Q amount, and it is inversely proportional to the 1 over surface area. That is much better, right?
Yes, uncle.
Because as you go away and away, the surface area would go bigger and bigger. So it is inversely proportional to the surface area. And
Yeah.
is inversely proportional to the epsilon. Plugging all this thing together, you get E is actually equal to the Q over epsilon A. Very simple. Then you can
Okay.
substitute the Q over epsilon. The A can be written as a 4 pi r squared, and rearranging that, the E vector will look like our Q over 4 pi epsilon r squared, and this can be written as 1 over 4 pi epsilon Q over r square. This is where we get back to the textbook formula or whatever the nonsense they say. This is K multiplied by Q over r square, where K is equal to 1 over 4 pi epsilon. Is that okay?
Yes.
But the understanding wise, I'm just saying this is the better way to understand. You get that? This is a better way to understand. Better way to understand. Is that okay? Any questions?
Yes. No, no questions.
Okay. So once we come to this point, now bring it in. I have a charge, call that as a Q1. It has generated a electric field. That is an electric field produced by the Q1 at a distance R is going to be written as 1 over 4 pi epsilon Q over R square. Is that okay? Q1 over R
Yes.
square. Now I'm going to bring in another charge here, which is a Q2. Then that will be, the Q2 will feel a force because of the electric field generated by the Q1. But now it is not simply a mass kind of thing. It is not a scalar quantity. In the mass case, we simply say that it will get attracted towards the center of the other charge. Do you get that?
Yes.
But in this case, what happens? We have 4 different scenarios, right? The Q1 can be positive and the Q2 can be either positive or negative.
Yeah, yes.
So if the Q1 is positive, means the electric field generated by the Q1 will be a positive electric field at the point Q1 is placed. And that would be felt like if the Q2, what we brought in, it will feel the positive electric field because of the positive electric charge Q1. Let's say the Q2 itself is a positive charge.
Yes.
That will feel a positive charge feeling a positive electric field will feel a force which will be a repulsive force. For the sense that, okay, I mean the Q2, what we are bringing in as the second charge will also produce a positive electric field, right?
Yes, uncle. Yeah.
So these two both are producing the same electric field. So to put it in a picture here, this Q1 will produce a electric field in this direction, getting away from that, right? The Q2 also, let's say this is positive, and the Q2, you bring in a Q2 here, that will also a positive charge. This will produce an electric field in this direction. They will oppose each other. Do you get that?
Yes, uncle.
So that will make the force felt by the Q1 positive charge because of the Q2 positive charge it will get away from the center of the Q. So this will be the E1 and this will be the F1, the force felt by do you catch what I'm saying?
Yes, uncle.
Okay, and similarly, the E2 direction positive electric field will be, but because of the other positive electric field, this will get repelled. That will be our F2 vector. Do you understand what I'm saying?
Yes, uncle.
Okay, so this is the beauty. So once we understand that, that is what we are talking about now. So it will be all included. That is not a problem at all because we are saying it will have its own direction. That's it. We don't now put it as a positive or negative. Depending upon the Q1 itself is a positive, then the electric field produced by the Q1 will be positive. It will be a negative electric field if it is a negative charge, Q1. Is that okay?
Yes. Yes.
Now, if you bring the Q2, that is going to feel a force. That force is called as force felt by the charge 2 because of the charge 1. It is called the electric force. Okay.
Yes.
That is going to be whatever the charge we brought in multiplied by the electric field produced by the first charge at that point.
Okay.
Is that okay?
Yes.
So the equivalent is from the mass, we are saying that a similar equivalent here is our charge. That's it.
Okay.
Once we start that and have the basic understanding, the mass is a scalar quantity, but the charge can be positive and negative. Because of that, we have much more beautiful things are happening here.
Okay.
So now
Yeah.
plug in the E1 value. So the Q2 multiplied by 1 over 4 pi epsilon Q1 divided by R square E1 cap. So this will be 1 over 4 pi epsilon Q1 Q2 divided by R square. For all purpose, I will write a new vector here.
Okay.
2 1 cap. You know why I do that? Because the Q1 and the Q2 will decide whether it is positive or negative, will decide the F21 cap. Because there are 4 scenarios, right? The Q1 itself can be positive or negative. Q2 itself can be positive or negative. Then the force felt by the Q2 charge, there are 4 possibilities.
Mm.
No, your U is not coming as a.
Yes, uncle. Yeah.
Do you catch that or not?
Yeah. Yes.
So that's why I just changed it to a. So put it this way, like, okay, so what I'm saying, even though the force I'm writing this as the 1 over 4 pi epsilon Q1, I would put it as a modulus Q1, modulus Q2. For example, I'm saying divided by R square, and there is a F21 cap. Now I take 4 different scenario. Case 1. That is, let's say there is a positive charge and a positive charge here. Then this would have produced, both of them would have produced here. So this is our Q1 and this is our Q2. And we are saying that this is also greater than 0. This is also greater than 0. Then don't you think that this will be our direction for our F2 cap, F21 cap? Do you get that?
It will, yes.
This center to center, both of them are producing this will be our E1 cap and this will be our E2 cap. As they oppose each other, the force felt by the second charge will be in that direction. Is that okay?
Yeah.
Okay, the scenario 2. Let's say keep this guy as a positive charge, the Q1. Still it is a positive charge, but this one is a negative charge, for example. It's a negative charge. Then what happens? So we can draw a line, this line. So now this Q1 would have produced a positive electric field and the negative electric field will be, so this will be the direction of the EQ2 cap. And this will be the direction of the E1 cap. Do you understand? Q1 is producing a positive charge which will be going away from the Q1. Q2 is producing a negative electric field which will be towards its center.
Okay.
Both are in the same direction. Do you get that?
Yes, sir.
Because of that, the force felt by the Q2 will be in this direction. So this will be our F21 cap. The negative charge will get attracted towards the positive charge.
Yes, sir.
Does it make sense for you?
Yes.
Okay. So if the electric fields are opposing, then the force will be an attractive force. That's the beauty. Do you see what I'm saying?
Yes, uncle.
Okay, so then there is a third scenario, which could be this guy can become a negative and this is positive. then this will feel a attractive force towards that. So this will be the attractive force, the F21 cap. And the last scenario is this can be also negative and this can also be negative. Then this will feel a repulsive force from. So this will be our F21 cap. Are you okay?
Yes, sir.
Okay, so there are 4 different scenarios. So that's why I put a new vector cap for that. But even we can include the E1, E2 cap also, but they are all going to play their own role. All we need to do is, if there is a positive charge, it will produce an electric field around that, which will be in this direction. You get that? Uniformly, this will be the drawing you will be drawing. So this is the electric field direction. Is that okay? So if it is a
Yes.
negative charge, you draw a line around that, but these lines should go into the center of the charge. So that's the diagram for the. Is that okay?
Yes.
So if you put, now I am completely isolating these two, but if you put something like a positive and a negative very close to each other, then this will start from here and it will end here. You see that?
Yes.
So this is how the electric field vector direction would be. And then it will go and it will get lower, and then it may go like that. You see what I'm doing?
Yes.
So exactly in the opposite direction, it will go up to infinity straight here. This will be a positive. So here it will be coming from, this will be so this direction is going away. Do you get that? So this is a kind of diagram. Makes sense for you?
Yes, sir. Yeah.
Okay, so this is what it is. So it will be from the infinity, it will go over here. So there may be a crossing point. So the understanding is, you see, this is going away and this is okay. This is coming in. Do you get that?
Yeah.
So they met at infinity, and then it is completing the loop in the infinity. Do you see that?
Yeah.
That is what we call asymptotically. Now it look like they are going parallel, but asymptotically they will meet somewhere in the infinity. That's the mathematical understanding. Does that make sense for you?
Yes. Yes.
Okay, so this will be the direction is. I don't want to disturb the other diagram. You get that? So this says this, the influence of the negative charge will be very weaker and weaker. Completely, it won't be there in the opposite direction. That's why it goes straight. Is it okay?
Yes, uncle.
Okay. So now once we have come to this point, now we have a job to do to go further with what is happening. So first thing is, I have not introduced to the different possibility. Let's say there is a mass M1 and there is a mass M2. And if there is a mass M3 also. Now what will happen? There will be, first of all, I mean, if you, okay, let's say, don't put the mass M3. Let's say we want to know the gravitational field generated by both the mass M1 and M2. Do you see what I'm saying?
Yes, uncle.
Okay, so I call that as let's put it as just a G itself. To solve this kind of problem, we need to do this is called superposition. Superposition. What this means, we should not try to do it both the M1 and M2, what is going to be the G value there. Rather, time being, keep the M2 separated, never bring the M2 in the picture, but this M1 would have produced a gravitational field in this direction, right? G1 cap would have produced in this, so that would create only because of so G1 vector is actually given by capital G M1 divided by whatever the R1 distance, R1 square multiplied by our G1 cap. You're okay with that?
Yes, uncle.
And the M2 would have created its own. So let's say towards this, it would have created in this direction, let's say the distance is R2 and G2 cap is the vector, then this would have created a G2 vector. It will be capital G M2 divided by R2 square G2 cap. Is that okay?
Yes, uncle.
So the resultant gravitational field strength G produced by these two masses at this point will be, this is a vector also, this will be G1 vector add with G2 vector. Vector addition of these two. Makes sense for you?
Yes, uncle.
To feel it, like now we know how to solve the problem. Let's say, if I mean, put it this way, let's say the M2 mass is completely not there, then the G2 will be gone, then only the G will be produced only by the, because of the mass 1.
Yes.
Then,
Yeah.
okay, the other way also holds good. If the M1 is not at all there, then the gravitational field is produced by the strength generated by the M2 will be only the G2 only. Is that okay?
Yes, uncle.
If the M1 is equal to M2 and the distance also R1 is equal to R2, then you will be adding the two equal amount of vectors and the resultant will be exactly in the midpoint. Do you get that?
Yes, uncle.
So it will be exactly. So this is a particular case where this will be the G direction. When you say that it will be 2 times G1 vector, also same as 2 times, no, not 2 times. Yeah, it's okay. 2 times our this direction. Okay, but this is not right. Okay, let me put it. We say that G1 magnitude is equal to G2 magnitude. That is the thing I want to mean. Is that okay?
Yes, uncle.
So magnitude wise, it is okay. So you can say that magnitude wise, it will be G1 add with modulus G2 is okay. Okay. Direction will be, the angle will be in the midpoint. We get that?
Yes, uncle. Yeah.
So it is something like, understand, vector under addition is very simple. Let's say you are talking about, let's say there is a vector in this direction and a vector in this direction. Let's say both are same equivalent vector, like a vector and a vector. Then the resultant, feel as if like this particular, think like there is an object and we tie two strings and we act same amount in this, then this will move along a direction which will be halfway through. Do you get that? This is where this will move. So this angle will be equal to this angle. Do you get that?
Yeah. Yes.
So to solve the problem, you will move this vector to over here and you move this vector over here. It will look like a square, because this will also be a vector, this will also be a vector, this will be a diagonal, then the magnitude will be root 2 our a vector. Do you get that? And the direction will be in this direction. Do you get that? Because this is a 90 degree, right? My diagram is not good, but they are equal means they will become a 90 degree and the diagonal will be root 2 times a. Is that okay?
Yes, uncle.
Any questions?
No questions.
Okay, so this can be used, is not only for our gravitational field. Any vector problem, if you have one displacement in this direction and another displacement in this direction, if this is our D1 vector and this is a D2 vector, then if you want to solve the problem, parallelly move this and parallelly move this, then the resultant displacement vector will be in this direction. Do you get that?
Yes, uncle.
This will be D vector is nothing but a vector addition of D1 and D2. So the meaning is, if the D1 is not at all there, then the D2 will be the answer. If the D2 is not at all there, D1 will be the answer. Do you get that?
Yeah.
But if they are equal, then it will be in between these two with the direction, and the angle will be exactly equal from both the vectors. but the magnitude will be root 2 times the one of the magnitudes, because they are equal, right?
Yeah.
But other possibilities also there. If the D1 is more than the D2, then the resultant will be more close to the D1. If the D2 is bigger than the D1, then the resultant will be, do you understand what I'm saying? Let's say there is a small vector and there is a big vector. Then you will be moving this parallelly to this and this is parallelly to this. Then the resultant will be more towards this guy. Do you get that?
Yes, sir.
Okay, that understanding, physical understanding should come. But in the other way, if you have a bigger vector here and a smaller vector here, then it will be more towards the bigger vector, the resultant. Do you see, automatically it comes with the, so that understanding should be there. So similar to that, now we know that there are vector quantities like our electric field, gravitational field, the gravitational force and the electric force. So as long as we know how to individually calculate the electric field of the, how many number of charges they are, then vectorial addition of them will solve the problem. Is that okay?
Yeah. Yes, sir.
So for example, they may ask a question like, if there is a charge here and there is another charge here, then let's say there is another charge here. So Q1, Q2, Q3. So what is the force felt, electric force felt by the Q3 because of the Q1 and the Q2? Then we can say that, okay, let's write that as a F3 vector is nothing but the force felt by the charge 3 because of the 1, add with vectorially the force felt by the charge 3 because of the 2.
Yeah.
That's it. So how to calculate the F31 alone? Then simply forget the presence of the Q2 at all. Then you can say that this is going to be 1 over 4 pi whatever the epsilon. Q1, Q3 divided by whatever the distance between them is R13 square. And there will be a unit vector along that direction. Is that okay?
Yes.
Okay, so that is going to be, depending on the Q1 and the Q2, Q3 value, it could be attractive or repulsive. That will take care of it. As long as we know what is the Q1, the sign of the Q1 and the Q3 will play the role. Is that okay?
Yes. Yes.
Similarly, the F32 vector can be written as 1 over 4 pi epsilon and Q1, Q2, Q3 divided by R23 squared F32 cap.
Yeah.
Okay, then that's it.
Yes.
So now I will give you a simple example. Let's say this is a positive charge. Let's say put a positive charge here and put a positive charge here. And this is going to be a negative charge. You get it?
Yes.
So connect these two to get a line which will be going in this direction outside, because this will be the direction for the F, because this is our Q1, this is our Q2, this is our Q2. See, this is Q3 and Q2. So the F31 direction will be in this direction.
Yes.
Okay, and connect these two center as it is a negative charge. This will be the direction of our F23 vector. Is that okay?
Yes, sir.
Okay, now if you want to find the resultant, parallelly move this vector and move this vector. So the result will be somewhat, this is the force felt by this is our F3 force, which is the vector addition of the 3-1 plus 3-2. That makes sense, right? Because the positive Q1 will repel the Q3, but the Q2 will attract. So that is why the F3 is in this direction. Do you see that?
Yes.
Okay. If the Q2 is really high, then it will be more towards it can go more towards the Q2. Do you get that? Compared to the Q1.
Yeah.
Or if the Q2 is much lower than the Q1, then it will go much towards this. So that is how we need to, when you solve it, it will automatically, direction will come like that. Is that okay?
Yeah. Yes, sir.
Any questions?
No questions.
Okay, I will stop here. We will continue the discussion more about that in the next week. Is that okay?
Okay. Yes, sir.
I have another
Okay.
meeting to attend. Okay. Okay.
Okay. Okay.
Okay. Take care. Okay. Bye.
Okay. Thank you, Amrut.
Yeah. Okay.